So what are we going to be talking about today? Biology of sand filters and the main problems you will get with biofilm. We will be talking about disinfection byproducts, how they are formed and how you can reduce them. And two of them, most importantly.
Yeah, this is really about trichloramines. As you all know, trichloramines, we go very much in detail. We also will talk about the trichloramines, the THMs, and here especially about chloroform, because this is what you will deal, what we deal here in Europe and you in the US, and also chlorates, which is maybe not so known in many countries. Here it's in the legislation, and it also makes sense that it is in the legislation, and we will tell you why.
Yes.
But we'll cover this shortly. We'll
Very
concentrate
shortly
on trichloramine and THMs.
Yes, exactly right. And then towards the end, as always, we will take your questions.
But there is something new.
Yes. What is new? New is that we would like for you to use the chat function here that we have. You can type in, go in here and all panelists, select all panelists and attendees. So everyone can see the questions. This will be easier for us to go through them and answer.
Because if you go on the Q&A, you don't see the question, we see it. And of course we can repeat them, but I think it's really easier for you if we go just for the chat function. Even if you do one on Q&A, we will go read it and answer it. But to make things easy. So we try to improve step by step.
Please don't be shy. Type your questions in. We're a small group. We're all learning here.
Raise your hands.
Yep.
Love to hear your comments.
Great. As always, our sessions will be recorded. You can watch them on our website. They will be there for a period of 7 days. After that, they will be replaced with the new session. You can also get the program for the entire 10 sessions here on our website. Plus, you will get a copy of the PowerPoint copies in a PDF form for you to download.
Yeah. And for all the ladies, I would re-watch the French version because there you have Florent, our marketing director, because he's 30 years, he's fantastic looking. And his French is excellent. Okay.
Better than ours,
yeah,
for sure.
Not hard to beat.
Okay. So what did we
Remember
learn?
last week, session about hydraulics. Let's summarize it in 3, like George Gammon from the US, in 3 simple steps. Step number 1.
Well, number 1, like you said, size matters, right? When it comes to the pipe dimensioning, consider speed, length, and turbulence. The lower the speed, the higher the pressure loss. So keep that in mind.
Yeah, it's really about the speed. You know, you go a little bit on the lower side if you have long pipe work, a lot of fittings. And the other way around, and that for really use the magic ruler. I know you don't have it yet.
No, not yet.
My small brother, Philip, actually he's 1 year older. You see that clearly, right? He will be responsible and promised until end of the 10th session, we will have this ruler in a US version and you will get it, right?
It will make pipe dimensioning easier than ever, huh? Step number 3.
So easy. Step number 3 was, well, that's a little bit my specialty. You know, for overflow pools, do not overflow them all the time. Overflow them really when you use the pool to have the best hydraulic. But maybe during nighttime, when you do not use the pool, go through the economy mode, reduce speed, do not overflow. You avoid evaporation and with this big energy losses. And last but not least, best is to backwash your pool directly, your filter directly from the pool and not through the balance tank. You save a lot of room, you save a lot of money. This money we can invest in variable speed pumps, flow wheels, bigger filters, AFM of course. So that makes fully sense. And it's like, you know, cleaning, you know, if you wash your hands, you want to wash it with clean water, not with dirty water. That's why.
It's a good idea.
Yeah.
So this was a chart actually, I think from the first session, right?
It was, yeah.
And what does it tell us? You know, we have 4 key elements when it comes to pool water treatment.
Yeah, and we were talking, you know, in session number 1, 2, and 3, mainly about these first 2 pieces of the cake, and all of them belong together. We were talking about pool hydraulic turnover rates. We were talking about pipe sizing. We were talking in session number 2 mainly about filtration. The lower the better, but you need a certain backwash velocity to have bad expansion to really to empty this bin. And that will result, let's forget about the fresh water, that's an easy one, in the disinfection. And with this disinfection byproducts, and there it can make such a huge difference. And this is what we stand for. You know, we want to have the lowest chlorine disinfection byproducts that you can have, because they're nasty, they're harmful, they're not good.
Mm-hmm. Okay, so this is our first topic, is biology in sand and the problems that you get with biofilm. Sean, you want to say a few words about this?
Sure, no problem. So what we're going to look at today in sand filters, or media filters as we like to call them, is how do bacteria that can very easily be killed by chlorine in most cases, how do they survive in a swimming pool? Well, and as we advance through the slides, they survive by attaching themselves to a surface, any surface in the pool, and then growing a layer of mucus or slime, it's actually biofilm, over themselves to protect against chlorine oxidation, or oxidation from bromine even. Even at extremely high levels of chlorine, the bacteria is protected inside this biofilm. So even 50 parts per million, for example, chlorine cannot fully oxidize the biofilm. It's going to try. It's going to use itself up trying to oxidize the biofilm, but the bacteria is going to be protected. And when the bacteria is protected in this biofilm, it can grow very, very rapidly. It's going to develop on the walls, the floors, the pipework, but especially in the media bed.
Yeah, there's a small animation over here that nicely illustrates this, right, John? You can see
exactly
how bacteria attach to the wall. As soon as they do, they produce this mucus, this slime, and chlorine's not able to penetrate. It's able to oxidize some of the biofilm, but it can't penetrate it, right?
Right. So this becomes a home for growing pathogens and other bacteria.
Yep.
You know, you might think, 50 ppm of chlorine, that will oxidize the biofilm. It will, to 99.999%, but because that's very, very high chlorine concentration, but not everything. If you have 1 billion of bacteria, and you only have 1 or 2 survivors, just James Bond guys or
the James Bond of the bacteria,
yeah.
They will survive.
And they can grow again very quickly. If there is enough food, good temperature, they double every 30 minutes. Out of 1, you have, within 2 days, you have 30 billions again.
Yep.
And that's really it. I mean, it would be wrong to say this would not oxidize, and you didn't say it, would not oxidize this biofilm. It will do this to a very big extent, but as you said, not 100%.
Yeah.
Only 99.99. And the thicker this biofilm, the more resistant it becomes against chlorine oxidation.
Yeah.
Right. Yeah. As the bacteria evolve so quickly or reproduce so quickly, they're also evolving and becoming chlorine resistant at the same time.
Mm-hmm.
So
where do they grow? Yeah.
Sure. Yeah. Like I said before, they're gonna be growing in the walls, the floors, any surface in the pool. Where we're focusing today is on the media bed. We've got a granular filter media inside a large tank, and this can represent approximately 90% of the total pool surface when you measure the surface of each granule. For example, 1 cubic foot of sand has a surface area of 1,000 square feet. And if we look at an example of a TR140C, for example, a 20 by 40 pool, 30,000 gallons approximately, with a flow rate of 83 gallons per minute. This is considering this a residential pool, 6-hour turnover time. We have 9.25 cubic feet of media in this filter. If we multiply that times 1,000 square feet, which is the surface area of 1 cubic foot of sand, we come up with 9,250 square feet of area on the media, okay? The pool itself, the walls of the pool, only have 1,400 square feet of area. So the media in this case represents 80%, 87% of the total surface area of the pool. So bacteria also like to grow in dark places. The inside of a filter tank is dark, and we've got 87+% of the surface area in the filter tank. So this is the most likely area for bacteria to grow, for biofilm to grow with the bacteria and to cause issues.
Mm-hmm.
And those issues are
what are the
coagulation
problems?
and the formation of channels. So if anyone here has ever changed the sand in a sand filter, you probably noticed clumps when you're taking out the sand. These are clumps of coagulated sand. It's coagulated with biofilm. When those clumps form, water can no longer flow through them. So we reduce the area, effective area of the filter, and make the water flow faster through these areas. Those are considered channels. They might not be visible in the filter bed like a wormhole, but they still exist because of the clumping. And when we do that, we know from the previous sessions that we're decreasing our filtration and efficacy and allowing those bacterial flocks to be discharged into the pool, making people sick. Also, we're going to notice increased turbidity because our filtration performance is reduced and it's no longer reliable. We can't trust the filter media to do its job that we expect. This is a great example of what a coagulated lump of filter sand looks like. And again, if you've changed sand in a filter, you've probably experienced this. If we eliminate the biofilm, we also don't have any clumping, we don't have any channeling, and we have reliable and consistent filtration.
Mm-hmm. May I add a few points?
Sure.
Excellent explained. You know, this wormhole channeling, you know, maybe it's only open for 15 minutes or maybe a day, you know, after a backwash it will close, but then it can form again. And if you have this channeling, you know, it's, as you said, not anymore reliable. You get this bacteria flux through. And what's the problem with this bacteria flux? You know, individual bacteria, planktonic bacteria, you easily kill them with a low chlorine concentration within a minute or half a minute. But when they are in flux, they're not anymore really sensitive. Then it needs much longer. And the second one, and I think that's also quite you in the US are quite aware about this. We are not so aware about this in Switzerland. Crypto. You know, if you have channeling, crypto will go through. Even if you do flocculation, whatever, if you have channeling, it will go through. So there is nothing to stop them.
Yeah.
So, I mean, to summarize means everything all the time. If you have turbidity in the water, it's not safe water.
Mm-hmm. Mm-hmm. So crypto, I guess, is 3 to 5 microns
3
in
to 5
size,
microns,
somewhere around there, huh?
We will talk very much in detail about this in session number 9.
Yep.
So please join us on this. And maybe another point to this. You know, we have seen 2 pictures. One that Philip showed, where you have seen, you know, on this electron microscope, you know, this grain of sand colonized with bacteria. This is like sand looks after 2-3 days like this. It will take a lot longer, 6 to 12 months, depending on the temperature, depending on the load, that it looks like here on this picture, you know, with the red cross. It really, that you have such a heavy biofilm that the sand grains really glued together. And this is where you get the channeling. And Philip will explain us this, why it takes 6 to 12 months, you know, to get to these conditions.
Okay, you want to go? You want to go that deep?
No,
okay, I mean we can.
You're my master.
Okay,
yeah.
So
yeah, sure.
We have.
That's why we are here.
We have heterotroph bacteria first that consume organics, and after a while you have the so-called autotroph bacteria that move in, that consumes the inorganic. So
and produce organics.
Exactly. So they start feeding each other, right? And that's when the whole dynamic in the filter bed really starts to go off.
And now comes some major things. You know, heterotroph doubles every 30 minutes, but autotrophs every 10 days. This is why it takes a lot longer until they come in. And this will match really your experience. You know, you change your sand and you're very happy for 3 to 6 months, you know, especially in warm water applications, baths, etc. You see it after 3, maybe after 6 months. In colder water, maybe after 12 months, where you see, okay, now it goes down, I have turbidity, etc. And this is why, you know, because they come in.
Yep.
Let me add a very last thing, and maybe I go too deep, I know. You know, sand really, it's a good mechanical filter, but it's also really good biological filter. You know, in aquariums and aquaculture, we use fluidized sand beds, you know, where you have sand and you bring the water from below and you always keep it in
suspension,
you know, where we grow a light biofilm, not a biofilm like here, you know, where they glue together. It's more like in your first picture, where you only have heated off bacteria, and which then reduce the organics from the water. And this is biofiltration. We don't need biofiltration, and we don't want biofiltration in pools. But for example, in aquariums, you know, to remove ammonia, for example, we want to have biofiltration. So first AFM filtration, followed by biofiltration, or the other way around. But this proves, you know, that sand is a perfect breeding ground for bacteria. They are better ones, but it's one of the best.
Yeah, it is.
And, you know, for instance, in Israel, a company called IDE, it's one of the biggest desalination companies in the world. You know, they also use sand filters, usually as biofiltration for pre-filtration and desalination. I think it's really not the best solution, but it can work.
Well, it might be a good solution there. It's definitely not a good solution for pools.
Not for pools.
Okay.
No.
So problem number 2, then, you just mentioned it, is it's a growth opportunity for pathogens, huh?
Okay, shall I take this? It's
my
favorite.
Sean, you can do it.
Hey, go ahead.
Or Sean?
No, go ahead.
If you can do it in less than 3 minutes, you can go.
That's challenging. Okay, so we have seen problem number 1 is this biofilm biocoagulation. Problem number 2 is really home for growing pathogens. And here, let me take out one of these, Legionella. Is Legionella something that you're afraid in America, Sean?
Yes, it is.
Okay. Definitely. Okay, short run through Legionella. You know, Legionella, first of all, as long as you drink them, you take them oral, not a problem. You can have thousands, millions. You will digest them, they're gone. But if you inhalate them, they can be a problem. Most of them are not a problem. You know, there are about 70 different species of Legionellas, and 60 for them are harmful. 5 of them you might get if you inhale them a Pontiac flu, which is quite a bad flu. But there is really the one, the Legionella aeruginosa, you know, where you can get very, very, very sick, which can be lethal, you know, if you have a weak immune system. It's a little bit like with COVID-19. Now, what has this to do with biofilm? You know, the biofilm is built up from the first guys here from the Pseudomonas. You know, they are building up the biofilm, and then later on a full variety of microorganisms is moving in. One of them is amoeba, and others are Legionellas. Amoebas, these are protozoan, I think it's called protozoan. Yeah, quite big animals, small, but compared to viruses or to bacteria, it's quite big. You know, and they are a kind of home for the Legionella. So Legionellas are a lot smaller. They are attacked by other bacteria. This is why they go to the amoebas. The amoeba are absorbing them, but they cannot. That's what we
see here.
That's what you see here. Yeah. But they cannot digest them. You know, they have a protective mechanism, so they cannot digest them. So if they are in the amoeba, they feel quite happy, and they double and double and double and double and double until the amoeba bursts. And then you have one shot, hundreds or thousands of Legionellas. So they really grow in a safe environment in the amoebas for this. What has it to do with the biofilm? How much do you have? 2 minutes 30?
10 seconds.
Okay.
No, you're good.
Legionellas can live in water or in biofilm, but not amoebas. Amoebas only can live in biofilm. So if you don't have a biofilm because you have a bioresistant filter media, you don't have amoebas. If you don't have amoebas, you don't have Legionellas. I'm not a biologist. This is all what I've learned from Howard. And, you know, that makes so much sense for me. And it really corresponds. I could tell some experiences. I will not do it for the moment. You know, which, you know, proves, you know, that Howard is 100% right.
Yeah. So did you learn this from Dr. Dryden or from Dr. Malcolm?
That was from Dr. Dryden.
From Dr. Dryden.
He's our Dr. Malcolm.
Okay, excellent. So problems with biofilm. First, leads to clumping, channeling, unreliable filtration. Second, biofilm is a home for growing pathogens. And the third problem we get with biofilm in a sand filter is that it leads to the formation of trichloramines.
This we leave to Dr. Meyer.
Yeah, okay. So,
or Sean.
Or Sean or me, I'll take this one. So this is what swimmers bring into the pool. Urine, sweat, skin cells, this all leads to, this is all summarized under urea, the term urea. Urea consists of mostly these 4 components here. The biggest one being urea, which is an organic molecule. It contains a carbon. We'll talk about this in a second.
Sorry to correct you, it's nearly like this. Urine and sweat mainly consist of urea. It's not urea consists from this. So the components from this is mainly urea, right?
Okay.
And urea, it's organic. You have this carbon in that you showed. It's nothing toxic. You know, urea is what you have in all your cosmetics, you know, to make your skin.
It's a big molecule. It stays in the water,
your skin
right?
gets softer, etc. And by the way, the 50 milliliters and the 200 milliliters, this is average numbers. They are peakers, spreaders.
Certainly
I'm one of them. But really, urine and sweat, 80% of this is urea, and 10% is ammonia, and then it's creatine, amino acids. I mean, forget about these other two; they're not important. We have 10% ammonia, inorganic, 80% urea, organic, and that brings back to Dr. Meyer.
Okay, so why is urea a problem in this context here? Urea enters the pool, and urea is the most important food source for our heterotroph bacteria that are now living in the biofilm. These bacteria will convert urea into ammonia. These are bacterial enzymes that do this conversion. So
that also corresponds that we said before. Heterotrophs take organics, produce inorganics.
Exactly right.
It's a perfect example.
Now we throw chlorine into the mix, right? Because our chlorine now in the pool will react with ammonia and will first form a monochloramine. Then it will continue to react into a dichloramine and ultimately in a trichloramine. And trichloramine is very light. It will get out of the water, discharge into the air very quickly. What is the Henry constant again? 435? Okay, so extremely light. Huh?
So the higher this number, the more volatile is it.
Now for this reaction here, for the reaction or for the conversion of ammonia into chloramines, especially trichloramines, it needs an acidic environment. For the mono and dichloramine, this will form at our normal pH in the pool between 7 and 7.4, right? But then the formation of trichloramine, which gases out of the water, really needs a very acidic environment. So the question is, do you ever have an acidic environment in a pool that is at 4 or 5 pH?
Yeah, that was actually also a little bit, you know, the criticism from other scientists who said, Dr. Dryden, is not right because, well, you don't have an acidic environment. And we have, because we have the acidic biofilm. You know, the bacteria, they excrete also an acid that makes the biofilm acidic. And the thicker the biofilm becomes, the more acidic it gets. So we have this filter bed. And we go with this in a low velocity through the filter where the monochloramine will go to dichloramine and then to trichloramine. This biofilm can have a pH of 5, 4, I think not much lower than 3, but it can be quite acidic. So we have a two-step process, the biological process forming urea into ammonia, that's the biological step. And then through the acidic biofilm, the step to form from monochloramine, trichloramine. I mean, the beauty from a water point of view, trichloramine will gas out, your combined chlorine in the water will go down, but you move the problem to the atmosphere where it's even worse because this is where you're smelling it. I mean, remember if you come in an indoor pool and say, oh, there's a lot of chlorine in the water. It's not the chlorine in the water, it's the chlorine in the air. If you want to smell the chlorine in the water, put your nose in the water and breathe in. It's not so comfortable, I wouldn't do it. But this is really what it is. You know, you don't smell the chlorine in the water, you smell the chlorine in the air, and this is trichloramine. But as a summary, sorry, I got too long.
No, so no biofilm means no or significantly less trichloramine. So what is the problem with trichloramines? First, as we just learned, trichloramines will gas out very easily. and they gas out, they get into the air, and they are very corrosive, they're very aggressive. So this leads to corrosion in the structure of the building. We have had instances here in Switzerland 30 years ago, maybe, or
even
maybe
more,
even
50.
more.
When I was young, I knew.
Where entire indoor pool ceilings came down, crashing down, actually killing people.
Yeah, 10 people, yeah.
Based on the corrosion that happened in the steelwork and the rebar, even within the concrete.
Yeah, and I think it was really, but easy to understand. If this is so aggressive against metals, it's also not great for your health, right? And this is what you probably will explain.
Not really, right? Yeah. So these trichloramines that gas out of the water are inhaled by bathers. They enter the lungs, and they are responsible for damaging the protection layer that we all have in our lungs, at least those that don't smoke too much, right? But this damages that protective layer. And really, and I think most of you know, we have something called Lifeguard lung disease, for example, in the US. There are studies out that 25% of athletic swimmers in the US will develop asthma at some point in their life. And this can be directly tied back to trichloramines. Not good for you.
Not good. No.
Huh? We know this.
Yeah. We also know from the dolphins, you know, that
if you live in the water, then it's especially not good, right?
Worse.
Yeah. So how can you reduce the formation of these trichloramines? You really have two options, right? You can either eliminate them, or you could prevent the formation of biofilm, because you cannot completely eliminate it. You have walls, channels, pipes, balance tanks, but really, as we learned, the biggest surface is the filter. And if we can eliminate the biofilm in the filter, we can eliminate the largest surface where biofilm is being formed.
Sure.
Okay, that's clear, I think. So again, in summary, eliminating existing biofilm, there is one good product that is very effective at doing this, is this chlorine dioxide. We will talk about this in session number 9, because it's able to actually penetrate the biofilm, while chlorine will oxidize it. But if it's thick biofilm, it will be difficult to get through, but chlorine is much more effective. The much better approach is a natural approach, an approach of preventing the formation of biofilm, which is the use of a bioresistant media.
I always compare this with cancer. You know, the left side with the chlorine dioxide, that's the chemotherapy. You know, chlorine dioxide, maybe even together with chlorine, that would be the best. You know, that's to eliminate this cancer. And that's session number 9. But best is you don't get cancer. You have such a strong immune system that you don't get cancer, right? And this is the bioresistance of filter media, and the best is AFM.
Okay, great. So this concludes the trichloramine discussion. Now let's talk about chloroform, right? Chloroform are also disinfection byproducts. They're part of what's called THMs. Let's talk a little bit about this. You want to take this?
Yeah, I love it.
You love this one, right? Yeah. So
one step before, you know, with AFM, I cannot promise you, ladies and gentlemen, my dear friends in America, that you have less of total combined chlorine. It will be more or less the same. I can promise you, you will have much less inorganic and much less of trichlorine, much less of chlorine smell. We can bring it down with other things that we will discuss in session number 8. But here on the chloroform, I can promise you, you know, if you have, especially our new AFM NG in, your chloroform levels will drop by 50%, at least. This is a blind promise. How does it come? You know, how is it formed? You have chloroform is always formed between chlorine and organics. Here you see an organic compound. You know, it's a long chain molecule. You have carbon, carbon, carbon surrounded by some other atoms. Most of them are hydrogen, right? Now we get in chlorine. Hypochlorous acid, chlorine. We will break up the double bonds of the carbons. You know, this is like one carbon gives here a hand and the other gives here a hand. You take one away, so you split this. And also UV, sun or UV light, medium pressure, you know, you crack these double bonds and you make these big molecules in smaller molecules. And the smallest molecules that you will end up is a methane, which is 1 carbon, 4 hydrogen. If now still you have chlorine in the water, you know, you will replace one of these hydrogen with a chlorine. You form chloromethane, and then a second one, dichloromethane, and then a third one, which is chloroform. So you have on this X methane, you have now 3 chlorine, and this is chloroform. This is also the reason why it's called trihalomethane. I always explain this very much in details because it took me 20 years to understand it. Now, since 10 years, I understand it. I'm so proud. I want to share this with all the world. Probably you're not interested, but you're on the call. Don't get out. Yeah, this is why we call it trihalomethane, because you have 1 methane with 3 halogens. And if you remember in the chemistry, you know, on the periodic system, the number 7 line, these are the halogens. This is fluorine, chlorine, bromine, iodine. And these are the chloroform, fluoroform, bromoform, iodoform. For us, it's really the bromoform and mainly the chloroform, which are important. And that means, on the other way around, as I said, you need organics and you need chlorine. Chlorine we have. If you remove 50% of organics, automatically we'll have 50% less of THMs. I mean, this is very logic. You remove 50% of the organics, you have 50% less of THMs. Too long?
No, this was good. You're getting better and better every time.
Yeah.
So this is good. So again,
I hope my wife would tell me this.
Well, let's not go there. So chloroform, as you said, is
about the kitchen.
Very volatile.
Yeah.
Yeah. You may have to do the dishes tonight at home, huh? Okay. And again, it enters the body through the lungs, and it will go into your nerve system.
It goes first in your bloodstream.
In your bloodstream.
You know, this is why chloroform is so much more dangerous than trichloramine. Trichloramine is nasty. You get asthma. But this really goes through your lungs, in your bloodstream, and then on your nerve system. Chloroform was the first anesthetic.
Anesthetic, yeah.
You know, you breathe it in. I mean, anesthetic, it was a good invention. You know, before you had anesthetics, you know, all the operation to cut off a hand or whatever, or to open, that was quite, yeah, you had to drink a bottle of whiskey and then it still was really, really painful. Mm-hmm. And, but with chloroform, you breathe it in. If you breathe in enough, you're knocked out.
So it's probably not very, doesn't make you any smarter either, huh?
No, definitely not.
Yeah.
No.
Yeah.
Like alcohol.
Like alcohol,
so it's like alcohol, just a lot stronger,
yeah.
right?
At least alcohol, you think you're smarter, but you're really not. So anyway, this, because it enters the bloodstream and the nerve system, this is particularly important for small children that don't have a fully developed blood-brain barrier. That's usually, you know, less than 2 years old, and also for pregnant women.
Yeah, yeah. And really, my dear American friends, take this seriously. You know, I really, there are countries like Croatia. You know, it's not the highest developed country. You can't compare it with the US. They only measure THMs. This is the only things they are interested. But really, chloroform is something which has to come to your radar. And especially, you know, these babies. I love babies. You know, they are the most vulnerable people. Humans that we have to protect them. And this is really not good. You know, it really can create severest damages. Dolphins, babies, pregnant women, this is really not good. And we really have to bring this chloroform down to the lowest point possible. For example, in Switzerland, we have in our regulation 20 microgram per liter, which is quite low. But you know, and if you are not sure, you know, and you have a baby or you're pregnant, don't use a pool, or really a safe pool, a daisy pool.
Yep.
This is really, you know, it's here, we are here also to make money, but this is really a moral mission to tell to the people, be careful with chloroform.
Moral obligation. And there are some good solutions, right?
Sure,
to this too, you know, that are not so complicated. So we're talking about the organic load that is directly responsible for the formation of chloroform. So a a very good way, or in order to measure the organic load, you know, you can measure either total organic carbon, TOC, you can measure KMnO4, which is really, KMnO4 is a very strong oxidant. So what you're doing is you're adding KMnO4 to get an indication of the total organic load that you have in the water. Did I explain this correctly?
Yeah, absolutely. TOC and KMnO4 is the same thing. It's a different kind of measurement. They are related. If you measure TOC and you multiply this with 1.5, you get to KMnO4. So it's just different measurement, but it's about the same. It's the oxidability, how much of KMnO4 or the other you have to add to the water until everything is oxidized. And the higher this number is, that means the more organics you have in.
Yep.
Yeah.
Okay. So, Sean, you want to summarize this?
Sure. It's pretty simple.
What is the solution?
Yep. How do we reduce the formation of chloroform? Well, we remove more organics from the water with AFM-NG, for example. Removing, as Dominic said, if we take 50% of the organics out of the water, we're going to have 50% reduction in the production of chloroform. This isn't something we measure in the US now, but we tend to see things from Europe trickle over to the US. So I would imagine in a few years, we're going to become more aware of chloroform.
Okay.
Another way to do this in combination with AFM-NG is, of course, use APF, the best coagulant and flocculant on the market. We're going to remove even more organics with that combination, again, even further reducing chloroform production.
So I think, you know, with AFM 50 and with APF another 50, so 75 totally, and that's huge. You know, if you have 75 less of THMs, we did something good. Yeah. We really did something good. And of course, water clarity and all the other things are coming in. I mean, other things you can do, shower, so you bring less organics in, or fresh water, but that's also not the perfect solution, but yeah.
You know, another
point has less organics than you have in the pool.
Yeah.
Very often here it's not the case.
Another point that applies very specifically to the US, you know, we don't backwash sand at the proper velocities normally. Generally, we're going to backwash it 15 gallons per minute per square foot in you know, the majority of cases across the country. And we know that in order to get the correct bed expansion and remove as much of the biofilm that's stuck in the filter as possible, we really should be at 20 gallons per minute per square foot or even higher than that. So in the US, we see the formation of biofilm occurring much more rapidly, especially in pools that aren't designed optimally and are not backwashing properly. We're not removing anything. It's just all staying in there. So, you know, and we'll talk about this in an example in a minute, but you go into an indoor pool and you swim for a while and you start to feel dizzy and you have a headache. Well, these are pretty common signs that you've been exposed to chloroform. So this is something to be aware of in the US, even though we're not measuring it. It's very important, and I think we'd all be we'd all have a huge benefit if we paid more attention to this.
If you get dizzy, it's time to do something.
Yeah, definitely. Yeah. Definitely.
But you're absolutely right. You know, filter is like a bin. You know, if this is AFM or sand, you know, you have to empty it, and you have to empty it properly. Otherwise, all these organics which are in the filter will still react.
Yeah.
So this is why we also recommend, you know, for AFM at least to backwash it once a week. I remember when I was with you in the US 3 years ago, you know, also one of our partners said, while we are backwashing, it's great you have AFM, only have to backwash it every 4 weeks instead of every 2 weeks or every 1 week. And I said, well, I would disagree with this because of the formation of trichloramines.
Yeah, exactly. Okay, so one other thing okay, here's a good example. Sorry, Sean, you want to talk about this as well?
Sure. Yeah, we have two examples from the U.S. A YMCA pool that one of our great dealers works out in, and they frequent the pool, they swim, they work out in the pool, reporting that they often felt dizzy, had headaches after they had worked out. We recommended AFM, of course. They're a dealer. They were able to have the YMCA install AFM. The facility immediately reported a significant reduction in the chlorine smell, or the trichloramines in the air, and that was immediate. And then the dealer followed up with us and said, I don't have the dizziness and the headaches anymore, and people that I swim with are reporting the same thing. So we would assume in this instance a reduction of THMs of chloroform as well. So that's an excellent case study, an excellent example of reduction of trichloramine and trihalomethanes. The Claude Moore Rec Center in Sterling, Virginia, took their competition pool that you see on the left and replaced sand with AFM, and they experienced such improvement in water and air quality. They're now budgeting it for all of their other pools, and they've got activity pools, water slides, splash pools for kids. So they've noticed the benefits in this large comp pool. They're really going to notice the benefits in these smaller pools as well.
Great. Thanks.
We have a moral obligation to change all these pools to DAISY, or at least to AFM.
Okay, one more thing we want to very quickly talk about
He is the expert.
Are chlorates. I don't believe chlorates are anywhere on the radar in the US. They're not an issue. We don't want to make them an issue, but they are an issue in some countries here in Europe. And we feel that it might be interesting for you to hear a few minutes about what chlorates are and what they do, because it might become an issue at some point. And so you have a little bit of a head start here from us.
It is a health issue, maybe not on the radar, but I think interesting. Let's spend 5 minutes on it.
Yes. Okay, so we're going to keep this very simple, but chlorates are formed by decomposition of hypochlorite. Chlorate concentrations vary greatly depending on the type of chlorine that is being used. The main problem comes from sodium hypochlorite, or liquid chlorine, or bleach also called. Hypochlorite will decompose, will break down based on time, heat, and sunlight exposure. And we have an example that illustrates this. I don't want to go into the details here of the different oxidation states. Before we tell you why that is, what is the problem with chlorate? Chlorate has a negative impact on your red blood cells transporting oxygen to the cells in your body. There's a substance, a molecule in the red blood cells called hemoglobin. Hemoglobin has iron, Fe2+, iron, which is able to attach an oxygen molecule and move this to the cells in your body. If you expose hemoglobin to chlorates, then the chlorate will oxidize the iron in the hemoglobin into Fe3+, which now will no longer be able to oxidize or to bind on the oxygen molecule and move it to the cell. So ultimately what it means is that chlorates are reducing the oxygen content in your body, and you're starting to get a headache. You're starting to get dizzy. And this is why chlorates can be a problem and an issue.
They're not volatile. You swallow them. They're not volatile. So if you don't swallow the water, it's not. But however, we have here some limits, and it's always good to try to reduce it. Mm-hmm. So how can we reduce them or avoid them? Well explained, by the way.
So I think
this is still an interesting one.
This is a good one.
Shall I do that? Yeah. Okay, here you have on the x-axis, you have the months, 1 month, 2 months, 3 months, 4 months. And here you have the concentration of the chlorine of bleach. You call bleach? Mm-hmm. If you store the bleach at 7 degrees, how much would be this in Fahrenheit?
7 degrees, that's like, that's cold, huh? That's 45.
45 Fahrenheit. You see in 4 months, you need 10% of concentration. But if you have 36 degrees, what is this in Fahrenheit?
90.
90. If you have
95.
In 1 month, ladies and gentlemen, you lose 50% of the concentration. You start with 120 after 1 month, after 30 days. If you start this, and very often we have this, indoor pool, you store it in the technical room. After 30 days, 50% is gone. On the opposite, you see here the pointed lines. You know, again, if you store the bleach at 36 degrees, you know, and you get it fresh from the production, you have maybe 20 milligrams per liter of chlorate in the bleach. After 1 month, this goes to 40. So you double the chlorate. And now you're in a situation where you have to double twice as much of bleach because the concentration of the available chlorine went down, and this what you're dosing has twice as much of chlorates. This is why really store it short and store it cold. Yeah, back to you.
Yeah, that's nicely summarized. I think most of us know that sodium hypochlorite breaks down quickly, right? Yeah. Loses active chlorine. I think what not very many people know that at the same time we are forming these chlorides, and,
yeah, and most people are not aware how quickly it goes down if you have high temperature or light. You know, light and high temperature is really the worst thing. Yeah. Maybe exactly this we jump because this we have not.
This is a product that we have here in Europe. It's called the Triton Aqua Generator. It's a hydrolyzer. We will bring this to the US a little bit later for discussion.
But still, we can add this. You know, also your salt chlorinators, especially if you run them at a lower salinity, you know, and you have this from Hayward, etc. You will have no problem with chlorates. Really, the problem that you have with chlorates is from sodium hypochlorite, from bleach, or also from cal hypo. If you go one more, I'm not sure if it's coming. Nope. No, it's not coming. However, you know, Philip said with cal hypo, you don't have the problem with chlorates. He is right and wrong at the same time. You know, as long as the cal hypo is as a powder and it's not in the water, no problem, because you don't have decomposition. If you dose the cal hypo, you know, with a machine, you know, if you need chlorine, it takes out this powder and mix it into the water. They don't have chlorates, very low numbers. And with salt chlorinators, very low numbers. But if you take 1 kilogram, so that's 2 pounds in 100 liters, that's 30 gallons, roughly, of water. You know, this is, or 4 pounds in 30 gallons of water. Then you have the same problem like with a bleach. With a bleach, you know, it can decompose. Yeah. So best solution would be salt electrolysis or cal hypo if it's mixed directly in the water. Not great is sodium hypochlorite.
Or chlorine gas.
Chlorine gas, but that's in a way, well, it starts to be abandoned here because of safety. Don't know how this is in the US.
So solutions to reduce chlorates, there are really 4 here. The first one is more fresh water, right? Which you bring in when you backwash, for example. Like you said, store bleach in a dark and cool place. It will extend or reduce the breakdown. 3, use less chlorine, for example, by reducing the oxidation demand of the water with a DAISY system. DAISY meaning AFM and the APF product, the coagulant flocculant that we were talking about.
Don't forget an outdoor pool ACO. That makes a huge difference.
And
you know,
ACO.
If you save 30% of the chlorine demand just by doing ACO, you have 30% less of chlorate.
Yeah, or use calcium hypochlorite.
Or directly mixed in.
Directly mixed in,
Or salt electrolysis.
Here we have some examples from Europe. I'm not sure, we're running out of time. We're going to skip these here.
Agree.
And we will summarize. Oops, now I went too far. No, that's correct. We'll summarize the key learnings from today's session in 3 simple steps.
Like George.
Step 1. If you have no biofilm in your filter, it means that you significantly reduce the formation of harmful trichloramines. So do not use a filter media that will biofoul. Replace it with a media that is resistant to biofouling. And that would be, for example, AFM. I don't know of any other filter media that is resistant, by the way. DE is also,
Yeah.
you're right. Yeah.
Yeah.
DE is also resistant.
Let's say fair, yeah.
Yeah.
DE.
Yeah. Learning number 2, less organics in the water means less formation of chloroform. So there's a direct correlation of organic load and the formation of chloroform. If you reduce the organic load by 50%, you will reduce the formation of chloroform by 50%.
Yeah, and that's really true. You know, short story again. You know, I'm a little bit storyteller. I was 2 years ago. I was in Croatia because I had a new customer who started to work with AFM, and he was not so well experienced. He was very well experienced in water treatment, but not so well experienced in with pools. And he said, "Listen, the only thing we have to focus is THM. We have to be below 100. Can we achieve this?" He said, "Easy. I mean, below 50, but below 100, easy." So he changed to AFM, and he did everything right. And he called me and he was very happy and said, "Dominic, we are, you know, we had before 400, now we have 20. He was very happy. 2 weeks later, he called me and he also gave me the Cayman of 4, you know, the measurement for organic load, which was very low, 3 or 4, very low. 2 weeks later, he called me and said, "Dominic, now we have 400. I said, "This is not possible. It can't be." Yeah, it is. Look at the analysis. So we were on a call with the owner and I told him, "Look at the Cayman of 4. It's still 3, you know, it's still very low. It can't be." And in a way, you know, this director, the owner of the hotel, he was a little bit angry with me and said, "Arrogant Swiss guy, how can he tell? I mean, it's an official lab," and said, "Please do me a favor. I pay for it. If I'm wrong, go to another lab and recheck it again." And they came back and said, 20. I was so sure I'm right because THM always go hand in hand with Cayman of 4, and that means with the organic load. If you reduce the organic load, your THMs will go down. Sorry. Step number 3.
Yeah, that's good. So step number 3, in order to reduce your chlorate concentration, store your bleach in a cool, dark place. Use Cal Hypo.
Short. Store it short.
Yeah. Use Cal Hypo, or in an outdoor pool, use ACO. Use ACO.
And right? Salt electrolysis.
Salt electrolysis.
Salt electrolysis, you don't give time for decomposition. So that's good. Yeah.
Okay. Outlook session 5. You know, the 3 of us, Sean, Dominic, myself, we are really Dr. Howard Dryden apostles in a way, right? Yeah. And we're going to introduce to you in the next session what Dr. Dryden has done, where he's coming from. You know, he didn't do what we're talking about here. He didn't do this for the pool guys originally, right? He did it for the dolphins. He's a marine biologist, and we're going to build that bridge so you understand where we are coming from and what we are talking about today for the pool industry.
Yeah, but today we can profit from his knowledge and his technology, talking about AFM on all the others. So we will talk about this very deep in session number 5.
Yep.
You have to hurry up. We
Looking
have
forward
some
to it. So this will be about activated filter media. What does it exactly mean? Why is AFMNG such a game changer?
Yeah, we will talk in detail about this, you know, what we changed, and it's really a game changer. You will see it. And filtration and backwash performance we already covered, but really about the NG and the new layering, the 50-50.